Section 4.7 is about inverse trig. So we're going to be combining two topics that we've already studied. One is trig, which we've just been doing. The other is inverse functions. And so I just reminded you here, we covered inverse functions in section 3.1. We did that right before we studied exponentials and logs, and that was because logs are inverses of exponential functions. Okay, now you might think at first glance that this would be a very short section, because let's just take a look at y equals sine of x. Now I know what that graph looks like. It's just my sine wave, like so. Okay. That's an arrow at the end. Okay, so it looks like this. This function is not invertible. Because remember, in order to be invertible, a function had to be 1 to 1. Now to be a function, we had to pass the vertical line test, so that each x value had a unique y associated with it. To be 1 to 1, we would have to pass the horizontal line test. A horizontal line picks out every point in the plane with a particular y value. To be 1 to 1, each y has to have a unique x associated with it. So if my graph intersects a horizontal line more than once, that's multiple different x values with the same y value. It's not 1 to 1. And none of the trig functions are going to be 1 to 1 because they're all periodic. If they're periodic, whatever they do again. They're going to hit those same y values again. So the graph of sine gives me the graph of a function that is not 1 to 1 and therefore not invertible. And so you might think, well, then there's no such function as inverse sine. But you would be wrong. There is a function called inverse sine. It's just not the inverse of this function because this function doesn't have an inverse. What we're going to do is we're going to create a related function, and we're going to do that by restricting the domain. So I'm going to graph the related function over here. What I'm going to do is I'm going to take just a portion of that graph. And as I figure that out, I'm going to be looking both at this graph. I'm also going to be thinking in terms of quadrants if I were to represent my angles rotationally. Remember, with this graph, here we're representing our angles as increasing as they move to the right. When I represent things rotationally, they rotate through the 4 quadrants. Okay. All right, so what I'm going to do is I'm going to restrict the domain by picking an interval that's going to correspond to 2 quadrants worth of angles. 1 quadrant where sine takes on its positive values, and 1 where it takes on its negative values. And that's it, so that I'm not repeating them. Okay. So if I think in terms of quadrants, the simplest quadrant to work with is quadrant 1. And of course, along this x-axis, there are lots and lots of intervals that correspond to quadrant 1. Because as we move along the x-axis, it's like we're going 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We're just rotating through the quadrants again and again. But the simplest version of quadrant 1 to work with would be the version that corresponds to this interval right here, from 0 to pi over 2. Because that gives me my acute angles. And with acute angles, I can work with right triangle trigonometry. So I'm definitely keeping that. So on my new graph, I'm going to include the portion of sine from 0 to pi over 2. Okay. Now that way, I'm getting a y value of 0, and I'm getting all of my positive values that sine can take on, and I'm getting them once. So I don't want to include any other intervals that would correspond to quadrants where my sine value is positive. But I would kind of like to hit the negative values. And so I'm going to take a look, and I'd really like to get a connected piece of graph. So I can say that I don't want quadrant 2 because sine would be positive there, and I'd be repeating my positive values. I'm going to want to choose an interval corresponding to either 3 or 4, but there's no way I can get an interval corresponding to quadrant 3 that's going to be next to an interval corresponding to 1. So I'm going to choose the quadrant that's adjacent. And again, there are lots and lots of intervals that correspond to quadrant 4, The one I want is the one that's right next to this one. So that's going to be the one that goes from negative pi over 2 to 0. That way, if I include that, I get a nice connected piece of graph. So here, I've got a new function. And here's the formula for the function. It's y equals sine x with a restriction that negative pi over 2 is less than or equal to x is less than or equal to pi over 2. Okay. So it agrees with the sine function when they're both defined, but if you gave me this function and said, what's its value at pi? It's not defined at pi, because that's not in this interval. So I've created a new related function by restricting the domain, and this function passes the horizontal line test. So this function is invertible. And when we talk about taking the inverse of sine, we're not taking the inverse of this, we're taking the inverse of this, which unfortunately means the inverse function is kind of poorly named, because it makes you think, if you call it inverse sine, you're thinking it's the inverse of sine. But it's not, it's the inverse of sine with the restricted domain. Okay, so here's how it is defined. I can say y equals, now there are two forms of notation for this, okay? It would be either sine inverse of x, or what I prefer is y equals arcsin of x. I prefer that for two reasons. One, people confuse that with an exponent. That is not the same thing as 1 over sine x. I'm not talking about the reciprocal. That would be cosecant. That's not what this is. So this right here is an inverse sine, not an exponent. This doesn't have that confusion. If I just say it's arcsin of x, that means the same thing. That's the inverse, not of sine, but of this function. Now here's the other reason I like going with arcsin rather than sine inverse. It's not just that it helps me to avoid a careless mistake of thinking of that as an exponent, but it helps me to remember, actually there are two more reasons. It helps me to remember that the output of this is going to be an angle. Because remember, when I'm working with inverse functions, what we're doing is we're switching the roles of x and y. So whichever notation I use, it means switch the roles of x and y, x equals sine y, and then these restrictions become restrictions on y. Okay. And if I put those two pieces together, that's going to tell me that y equals arcsin of x is the angle. So y is the angle. It's the thing I'm plugging into sine in the interval from negative pi over 2 to positive pi over 2, whose sine, whose trig ratio is x. And while there isn't going to be a unique angle whose sine is any given number, there will be a unique angle in this interval with that sine. Okay. So the arc here, well, if I remember that the radian measure of an angle is related to the arc length, this helps me to remember that the output of the inverse trig is the angle. We're switching the roles. So with regular trig, you plug in an angle, you get out a ratio. With inverse trig, you're going to plug in a ratio, you're going to get out an angle. Okay, the last reason, and this is the fun one that I prefer this, is that, again, people tend to think this means the inverse of sine, and that causes all sorts of confusion, okay? But it's the inverse of this function. It would be nice if we gave this a different name. I had a student one semester who said, why don't we call that sine and just put a little r next to it to indicate that it's got a restricted domain. So this function is sine with a restricted domain. Brilliant. Unfortunately, the notation's been set in stone, and it would be difficult to get that adopted, so that while I think that would be great, you could use that notation, and once you left this class, nobody would know what was meant. Okay? But if I pronounce arcsin, I'm saying the word arr. I get to talk like a pirate, and it reminds me that arcsin is not the inverse of sine, but it's the inverse of sine with the restricted domain. Gotta love it. Okay, so make sure you talk like a pirate when you're doing inverse trig. Okay, so that's how we are going to define our arcsin. I am going to use this notation, and I would encourage you to use this notation as well. If you're already used to doing inverse trig and using this notation, it's perfectly correct. You don't need to change. And if I'm working with you one-on-one and you prefer the inverse notation to the arcsin notation, that's totally fine. Just let me know and I'll adapt to what you prefer. But throughout this section, I'm going to be using the arc notation because I do think it's better notation. Okay, so if that's how we define it, let's now take a look at how we would evaluate it. Okay, so let's say I want to evaluate arcsin of 1/2. Okay. Now what I find it helpful to do is give that a name that makes me think angle. So I'm going to call it theta. That makes me think angle, okay? And I'm trying to figure out what theta is. And I'm just going to rewrite this in a form that's more familiar to me. I know this tells me that sine of theta has to be 1/2. Now that equation by itself would have infinitely many solutions. But I also know that theta has to be in the interval from -π/2 to π/2. Now that's going to be in either quadrant 1 or 4. So I'm going to take a look at this and I'm going to say that's a positive number. Sine would be positive if I'm in quadrant 1. Okay. If I were in quadrant 4, sine would be negative. So the plus or minus sign of the value of the trig ratio is going to tell me which of the two quadrants I'm in. Then I can look at the absolute value. If I'm in quadrant 1, I know we're talking about just an acute angle, and I know that its sine has to be 1/2. Okay, I've seen that before. I'm going to just jump to my 30, 60, 90 triangle. 1, 2, root 3. Which angle has a sine of 1/2? 30 degrees. But my answer isn't 30 degrees. My answer is π/6. By definition, theta is the angle between -π/2 and +π/2, whose sine is 1/2. 30 is not in between these numbers. So when you're using inverse trig, by definition, the output is in radians, unless otherwise specified. Now there are times when you want to use inverse trig, but you want to be working in degrees, and then you can say, I'm using inverse trig, but in degrees. Okay. However, do be careful. On calculators will do inverse trig in either radians or degrees. Whatever mode you're in, that's how it's going to do the inverse trig. So if you're using a calculator and it wasn't specified that you're in degrees, make sure that you're in radian mode as you're using a calculator for your inverse trig. Okay, we've been going for a little while, so what I'm going to do is give you a couple of ones to evaluate, and then we'll do that together in the next video. So I want you to evaluate arcsin of -√2/2. And you should be able to do this without a calculator. There are certainly values I could give you where I wouldn't know how to do it without technology either. But I'm giving you ones that you should be able to do without any technology. And also evaluate arcsin of -1. So try those two, and we'll go over them together in the next video.